Now I'm going to be starting off, I'm going to be kind of interspersed between things, and I am going to be talking about some of Einstein's greatest hits and misses. Because obviously Einstein's been in the news recently because of the gravitational waves. Hands up anyone who heard about gravitational waves. Give us a cheer. Yeah. Hands up anyone. Give us a cheer anyone who's really confident in knowing what gravitational waves are. On the count of 3. 1, 2, 3. That's okay. Gravitational waves are complicated. You can say, oh, there wobbles in space-time, but really it's a matter of Einstein's general relativity. But general relativity is kind of what he did later on. He started off with special relativity. It wasn't special because he'd come up with it and gone, this is amazing. It was special because it only applied to special cases. It didn't include gravity or acceleration. So missing out quite a big part of the universe. But as well as that, he's also well known for so many other bits of physics. And relativity is kind of like one of the foundation blocks of modern physics. And the other kind of big one that you may have heard of is quantum physics. It's quite embarrassing actually, because we've got these two foundation blocks, and they're both brilliant theories, but they don't quite match up in the middle, and we haven't worked that out yet. That's something that we're still trying to think about. But Einstein was there kind of for the start of both of those. In fact, Einstein won his Nobel Prize not for relativity, not for gravitational waves, nothing at all about that. He won his Nobel Prize for his explanation of an electric current. Not just any electric current, it was an electric current that you got when you had just a metal plate as part of a circuit, and then a gap, just a vacuum, nothing at all between that metal plate and the rest of the circuit. And what he did, well, what other people have done, is shown that if you shone light onto this metal, the electrons would be able to escape. They would get some energy from the light, and they would go whizzing off away from the plate and go around and get into the rest of the circuit and complete the circuit. But there was a problem, because everyone was quite happy in those days thinking that light was a wave. And we've got all these equations, Maxwell's equations, which described how electricity and magnetism work together to produce these light waves. And that said that the energy was given basically by how bright the light was. Like the brighter the light, the higher the intensity, the more energy there was there. So you think more energy, we'd be able to get the electrons flying out with more energy. But that didn't happen. In fact, for some colours of light, no matter how bright the light was that you shone on this metal plate, no electrons would be able to get out at all. And this was very confusing. What making it brighter did do was increase the number of electrons, but not how quickly they were going across this gap. And what Einstein realised is that, based on someone else's theory that previously, which suggested that things might be quantized, which basically means effectively come in lumps. That's what quantum theory means. It's basically lump theory or bit theory, whatever you want to call it. But he realised that the different colours of light gave energy in different lumps. And your lump of energy, your quantum of energy, your photon of light had to be big enough in order so that one of those could knock an electron out of the metal. If it wasn't a big enough lump of energy, the electrons just kind of wobbled a bit and stayed in there. And it's really, really difficult to hit the same electron with two different particles of light at a close enough time for them to escape. So that just didn't happen. And this kind of idea of light being made up of these particles, these photons, is something that we've used so much more. It can knowing how this works has led to things like lasers, street lamps. Street lamps, the old sodium street lamps, you wonder why they're that kind of weird yellow colour and everything looks weird and yellow underneath them. That's because they're giving out light which has a very specific amount of energy per particle of light, which corresponds to yellow. And so because they've only got that colour of light, obviously you don't see any others. But we can do something even more interesting with knowing about these colours of light, because that yellow comes from the sodium in street lamps. And different elements will give you different energies of light coming out when you excite them with electricity or whatever. And so we can look at, say, the gases around the sun and see which sizes of energy, which size photons are coming out of those, which colours of light. And that will tell us something about the energy inside the atoms, inside the gas that's surrounding the sun. And that will enable us to know what gases there are around the sun. We can tell that. But even better than that, we can look at this in distant solar systems, other stars. We can see basically how the light coming from those is different, and where there are gaps because basically it's all that, those photons of light are getting absorbed by the gas around them. And then we can know what elements are surrounding those stars. And we've gone one step further than that recently, and we can now see the gaps, the types of light that are missing because they're getting absorbed by the atmospheres of planets in other solar systems passing in front of their star. And all this can be traced back to Einstein wondering how on earth his electrons were coming out of this piece of metal. Thank you.